Welcome to Relativity Part 3. Today we're going to look at length contraction, how velocities add up relativistically, because we know they don't add up just algebraically, and we're also going to look at relativistic momentum, so how something's inertia is affected by its relative motion.
What do we really mean by near and far? In a way, distance is just a measure of how hard it is to get between 2 points. The harder to get from here to there, the more distant there is. This makes thinking about distance in multiple dimensions easy. In 2 spatial dimensions, a point a mile north and a mile east is more distant than one that's just a mile east. It's harder to get to. What about 1 space and 1 time dimension? Piece of cake. Getting to a point a mile east in a minute is a lot harder than getting there in a day. So 1 mile east and 1 minute in the future is way more distant than 1 mile east and a day in the future. And a point that's a mile east right now is impossible to get to, so it's super distant. But hold on, that would mean that a minute is farther away than an hour. Doesn't that seem backwards? It kind of is, but that's the way the universe works. In special relativity, more time equals less distance. So distance in time is negative. And if you travel east and into the future in such a way that the negative time and positive space distances cancel out, your total distance will be 0, and you'll be traveling at the speed of light. So how far away is tomorrow? It's closer than you think.
As objects move through space-time, space as well as time changes. In a nutshell, space is contracted, making the objects look shorter when they move by us at relativistic speeds. This length contraction was first proposed by the physicist George F. Fitzgerald and mathematically expressed by another physicist, Hendrik A. Lorentz. Whereas these physicists hypothesized that matter contracts, Einstein saw that what contracts is space itself. Nevertheless, because Einstein's formula is the same as Lorentz's, we call the effect the Lorentz contraction. Where v is the relative velocity between the observed object and the observer, c is the speed of light, l is the measured length of the moving object, and l sub 0 is the measured length of the object at rest. Lisa Lorenz holds a meter stick and sees another meter stick whiz by her at 87% the speed of light. She measures the moving stick to be contracted to half its original length. If the stick were moving at 99.5% the speed of light, she'd measure its contraction to be 1/10 its original length. If the stick were somehow able to move at c, its length would be 0. This is one of the reasons we say that the speed of light is the upper limit for the speed of any moving object. Interestingly, contraction of any object takes place only in the direction of motion. As the speed of this horizontally moving baseball increases, length in the direction of motion decreases, but lengths in the perpendicular direction do not change. No contraction takes place vertically. Here's Lisa Lorenz again, holding her meter stick as a spacecraft whizzes by. We see 2 parallel meter sticks. Which is contracted? From Lisa's frame of reference, she sees contraction of the spacecraft meter stick. From the point of view of an observer in the whizzing spacecraft, Lisa's meter stick is contracted. So relative to Lisa, the spacecraft stick is contracted. Relative to an observer in the spacecraft, Lisa's meter stick is contracted. So again, which is contracted? Our answer is that it's all relative, and there's a nice lesson to learn here. The effects of relativity are always attributed to the other guy. Length contraction should be of considerable interest to space voyages. The center of our Milky Way galaxy is about 25,000 light-years away. Does this mean that if we traveled in that direction at the speed of light, it would take 25,000 years to get there? From an Earth frame of reference, yes. But to the space voyages, decidedly not. At the speed of light, the 25,000 light-year distance would be contracted to no distance at all. The imagined space voyages would arrive there instantly. For hypothetical travel near the speed of light, length contraction and time dilation are just two faces of the same phenomenon. If astronauts go so fast that they find the distance to the nearest star to be just 1 light year instead of the 4 light years measured from Earth, they make the trip in a little more than 1 year. But observers back on Earth say that the clocks aboard the spaceship have slowed so that they tick off only 1 year in 4 years. That's of Earth time. So both agree on what happens. The astronauts are only a little bit more than a year older when they reach the star. One set of observers say it's because of length contraction. The other set say it's because of time dilation. Both are right.
With time dilation and length contraction together, we can now see the final solution of how Einstein's postulate allows the two starships to measure the same speed of light. As the upper starship passes, we see that the starship's clock runs slower than the one at rest. We also note that the starship itself is shortened or contracted. After 12 seconds elapse on the stationary clock, we see that only 9 seconds elapse on the moving clock, not the 6 seconds we assumed in an earlier example. But due to length contraction, the moving ship and all the rulers aboard are contracted just enough to make the measurement work. According to the crew, the beam of light travels 9 light seconds and 9 seconds. They now report that the light beam travels at the correct speed of 1 light second per second. These unusual effects of relativity, time dilation, and length contraction depend dramatically on your velocity. At everyday speeds, they are simply not noticeable. The fastest that humans have ever traveled is a few miles per second, a tiny fraction of the speed of which light travels, 186,000 miles per second. But in Einstein's universe, space and time are no longer absolute. There is no single time that exists for everyone in the universe. No distance in space that everyone can agree on. Space and time, like classical velocities, are only relative.
You know that if you jog at 1 meter per second atop a train bed that moves at 10 meters per second, your speed relative to the ground is 11 meters per second. The two speeds simply add. And you know that if you jog at the same speed of 1 meter per second in the opposite direction on the moving train, your speed relative to the ground is 9 meters per second. Here you subtract your 1 meter per second speed. But are these numbers correct? The 11 meter per second and 9 meter per second speeds? Well, guess what? Not quite. What you know is almost correct. Taking special relativity into account, these speeds are very nearly, but not exactly, 11 meters per second and 9 meters per second, respectively. Strictly speaking, this common sense rule is an approximation to the relativistic rule for adding velocities. I won't go through the long derivation, but simply state the rule. V equals the sum of the velocities divided by 1 plus the product of the velocities divided by c squared. The numerator of this formula makes common sense. But this simple sum of two velocities is altered by the second term in the denominator, which is significant only when both v sub 1 and v sub 2 are close to the speed of light c.
Alright, so I hope you enjoyed those presentations, and I will see you in class.